So I don't know if you guys looked at the homework problems, the recitation problems, and the homework problems. You'll see that they're kind of similar, which is the intention of the recitation. It is to help fill in whatever gaps you might think you have between what's being taught in the lecture and what's in the homework problems, and just to help you maybe understand them better with some more examples. If you don't know, I'm Tribhi. I am a PhD student in robotics. I work with Professor Mani. And we're gonna start the recitation. Are we good? Everyone set? Yeah? Okay. So the first set of questions I think that you'll find in your homework problems, at least in the drill solutions, is for linear systems. Now, a linear system is simply a system of equations with no nonlinearity. So you wouldn't see a term like a cosine of a variable or logarithms or powers more than one. And you'll see that these systems are equally as relevant to us as more complex systems, because a lot of the times in engineering, we end up approximating all nonlinearities to a linear system because we can get good solutions from the methods that we learn in this course. So let's get started. So I prepared 3 types of questions which I found in the homework problems, and I gave, I think 3 examples for each of them. For the interest of time, I don't think we can go through all of them together. So I want you guys to pick one problem that you like, and then we can go over it together. Does anyone have a preference, or should I just pick one at random? Preferences on the remote side? Should we just take up the first one? Yeah, that sounds good as any. Cool. I'd actually give you guys some time to solve it if you want. It's better than just me rambling on about what the solution is, I guess. Do we have a solution? I'm sorry, you're the only person in class. I feel like I'm bullying you, but you're it. Mm-hmm.
neighborhood problem.
Yes, correct. So our solution is 14 by 5 and 8 over 5. And I'm going to go over it just so we are consistent on how to solve it and people online are able to follow. So the general way of approaching solving a system of equations is simply you dive into it. So your step 1 is you find y in terms of x from any one of these equations. So let's say choose equation 2. So you put y is 2x minus 4 Next step will be you substitute your solution in equation 1. So you get x plus 2 times y, which is 2x minus 4 is 6. And then that becomes x plus 4x minus 8 is 6. And then 5x is 14. Then you get x is 14 by 5, which is what you got. So there you are. The final step is then we find y from the value of x that we just got. So you get y is, we're going to use this equation, and you get 2 times 14 by 5 minus 4, which is, quick math, 28 by 5 minus 4, which is 8 by 5. So our solution is unique. There was no contradiction at any point, and we found 2 specific values of x and y. And now we're gonna also try to sketch it on a graph. So let's go to a graph part of the problem. Yep. So let's try and sketch it, which is how, I think it's in one of our homework problems as well. So I'm gonna write our equation on top over here. So our equations are x plus 2y is 6 and 2x minus y is 4. And our analytical solution that we just found is 14 by 5 and y is 8 by 5. And now we want to see if we can get these same values by plotting them. Did you find the plotting paper? Yeah? Okay, good. So, let's do this. So, first step will be you want to write your equations in the slope-intercept form. So y is mx plus c. So the first equation, this becomes y is minus x by 2 plus 3. The second one becomes y is 2x minus 4. Following? Everything good? You guys, everything good? Maria and Ansh? I'm gonna assume everything's okay. So then, these are still the same equations. How we want to plot is we want to get 2 points on each of these lines and then join them. The other way would be to get the slope, find the angle that it makes with the x-axis, and that angle is given by tan theta is equal to m, but that's harder to write, that's harder to find out, and the easier way is just to cheat, get 2 points, and just draw a line through it. So in 1, how you would get points is, let's say you put in the equation 1, put x0 and x6. So then you would get y equals y equals 3, and when you put x equals 6 in 1, and in 2, I'm going to do the same thing. I'm going to put x equals 0, and I'm going to put x equals 2. And you get y equals, and y equals 0, right? So basically we found the x and the y intercepts because it's easier to plot it that way. So your points for the first line are 0, 3 and 6, 0, and for the second line are 0, minus 4 and 2, 0. Now let's try and find these points on our plot. So 3, let's start with the second one. So 0, minus 4 means this point. And 2, 0 is this one. A line that goes through these points will hopefully go like this, right? And then similarly you get 0, 3 and 6, 1, 2, 3, 4, 5, 6, 0. Hey.
Sorry about being late.
That's okay. Do you want to grab a wipe and one of the sheets? Your name?
What did you say?
I just asked you your name.
I'm John.
John. Okay. Hi, I'm Tribi. So, let us get back and John will catch up. So the line through this plot will be like this. So then we have an intersection point right here. Do you want to guess what that point is? But how do you get it from the plot? You can't see 14 by 5. Yeah, but how do you know? If you were to just look at the graph, you'd say it's like, I'd say it's 2.8 comma 1.8. No? Yeah? And what is 14 by 5? In decimals, in big boy numbers. What is 14 by 5? Yes, it's 2.8. And 8 by 5 is 1.6. So we're like 0.2 off because my drawing's bad. But the idea is to be able to see that you can find a unique solution from the system of equations. You can either plot it or you can analytically find the solution and they should match up. Did we prove it? Yes, we did. Okay. I feel like I'm boring you guys with this now, so I'm going to move on to the second set of problems. And you find problem part B and part C were, when you solve it, you find no solution and one example of infinitely many solutions. We'll post the solutions of both these problems on the Canvas website for everyone. Okay, so good. Should we move on? So we go to determinants. So we talked about these 4 facts about a determinant. One is that it is a real number. Another thing we know about a determinant is that for a system that is written as AX is B, which is the system of equations that we're going to try and solve, with A being a square matrix, which means there's n equations and n unknowns. So we know that it'll have a unique solution for any B if and only if A is not rank deficient, which means the determinant of A is not 0. If it is 0, then it can either have infinite or no solutions. And we don't know how to differentiate between the two, but that's all the information that the determinant is going to give us. So, how you'd want to arrange your problem in AX equals B form, and we'll find multiple ways of solving this throughout our course. But before you do that, you want to know if there's a unique solution to your problem. So you want to be able to see if the determinant is in fact not 0. So the way to arrange a linear system of equations into AX equals B format is first we stack our vector of unknowns. So we first find the vector x. So for the first problem, that would mean the x vector the notation is a little ambiguous, but that's how people do it. So your x is x and y, Your B vector is simply, you move the constants to the right-hand side, which is already done for you in this example, and then you stack them in whatever order you like. You can either put the first equation first or the second one first. It's all up to you. I'm going to keep them in order for this one. And from there, we find the coefficients of our vector of unknowns. So for this problem, that will be, you go. Yep. Yep. Perfect. And then the determinant will be,
-5.
yep. So it's 1 times -1 minus 2 times 2. And that is -5. So we note that the determinant of A is in fact not 0, which means we have a unique solution, which is what we had here. It's the same set of equations. Okay. So, do you guys want more examples of this, or are we good on the linear systems part? We're good?
I'm good on that part.
Okay, perfect. Everyone here is good? Maria? I don't know if they're still here. Okay, so we're good. So I'm going to move on from that. How are we on quadratic equations? We're good? Okay. How do I get the chat back? People online, how are we on quadratic equations? Do you want me to skip on, go to Julia so that this is more informative for you, or should I go over one example from quadratic equations? Yes, Julia. Okay. Maria? Okay, I feel like you guys already know quadratic equations, so this will just be boring for you. So I'm gonna skip ahead, but questions, if you guys have any of these questions, office hours or Piazza, or there's a myriad of other sources. So, since we're all here for Julia, we will go to Julia. Okay. Cool. So I'm not gonna take up a lot. I'm only gonna take up like a gentle introduction to what Julia is. And hopefully I'm gonna try and motivate why all of us are just going towards Julia now. So, a little bit of history. Julia is kind of new. It was introduced in 2012. It was like a side project of this group of engineers who were developing a programming language for their project, and it just turned into something big, and they just stuck with it, which is how best projects start. Over time, it's gained a lot of popularity, especially this year. There's been 17 million people that have downloaded Julia from their website, and they're kind of proud of it. Their co-founders are very vocal about how much they like Julia. In fact, just because we have the time, do you guys want to look at this shorter lecture? So this is basically one of the can you see? Look at the captions.
Let me ask, perhaps by a show of hands from the audience, how many of you know what a programming language is? Okay, this is MIT after all, so maybe I shouldn't be surprised. How many of you have programmed? Okay, this is a great audience. This is MIT. So I'm the co-founder of a programming language known as Julia. Perhaps some of you have used it. And this language is becoming increasingly popular for all of the various kinds of models that will be coming up in the various talks today, the climate models, the economic models, the various political models, and so forth. So let me say a little bit about myself, first of all. I'm a mathematician. I'm a computer scientist here in this building. I mentioned that I'm a co-inventor of the programming language Julia. I have a wife and 2 children and the cutest little corgi on the planet, so you might see him around here. What I'm not, to be honest, I'm not a climate scientist, I'm not an economist, I'm not a policymaker, I'm not even completely sure why I'm even in this room, except we are all on this planet together. So, about programming languages, humans talk to computers specifying the instructions that automate our world with programming language. The climate models, the economic models, the political models, they're all implemented as instructions to computers. I co-founded this programming language, Julia, that allows not only humans to talk to computers, but it allows humans to talk to humans about their intent on the computer. So we all have this vision of, we program a computer, maybe you sit in your own little room in a little silo somewhere, and you specify these arcane instructions that you tell the computer what to do. I have a vision of the ability to have other humans know what it is you're telling the computer and what they can do. You might think that it's a common occurrence that programming languages can, somebody writes a program and another person can look at it and see what's going on. But I assure you, it's anything but. I've taken a look at some climate models, some of the codes out there, and I assure you it is very, very, very difficult for a human to find out what is going on in those models. Perhaps you've programmed. Many of you have raised your hand. There are languages out there that some of you may have heard of, like Java and C++. These are languages that are very, very common in the business world. There are other languages that are easy to use. There's Scratch. Python was invented as a language to become easy to use, and because it was so easy to use, it became extremely popular, and now it's very, very widely used. So the common wisdom has always been...
So I'm going to stop here. So the takeaway, the whole idea of watching the video, is just that you want to motivate Julia as a programming language and why it's becoming popular over the years. And the crux of the problem is that it's easy to use, it's easy to write. You can share your code in a way that other people will understand it, because when you're writing your code, it looks very similar to how you would write down a math problem. So you don't really need somebody to be an expert in programming to understand your code, which is a very good thing that a lot of other programming languages are lacking. And at the same time, you'll see that MATLAB can do that, but at the same time, MATLAB is super slow when it comes to heavy computations. So somehow, Julia got the best of both worlds, and they gave us a programming language that you could use for real time, for systems in real time, and also have it be such that it's easy to write into and it's easy to understand. So how we are going to program in Julia is we've given you a Lumidesk. If you've looked at it on your Canvas web pages, you don't have to worry about a local installation, but there's a link of a video in here which is very easy to follow, and you can set up a Jupyter Notebook installation for yourself on your local PC. But for the purpose of this course, we've installed all packages for you in a neat Lumidesk Docker kind of server. You don't have to worry about what a container and Docker is. It's a web server that allows you to run Julia on it. Your computer is using none of the computational stuff is being done on your computer. So you're good, you just need a good internet connection. This is where we break into a demo. So I'm gonna open my Canvas page because we're getting questions about how to access a Lumidesk. So you open your Canvas page, you do your login, and you open the Rob 101 page. In this tab, you'll find Lumidesk. Now, it will be tempting to go to Create Your Notebooks, but it will not let you because you don't have access. Go to Start My Server. Finally, because this is a fake account I created, there's no notebooks in here yet. What you want to do is you want to go to Assignments and you want to fetch this assignment. And then you go back here and maybe just refresh it. And you see that this folder is here. You go here and only homework 1 is available. So we click on homework 1 and then we click on the notebook and it opens in another tab. Now, if this is the first time that you're using Jupyter Notebooks, what makes it easy to use is basically if you know how to, there's one way to just run these cells from, let's say I use the run button and it'll go to the next thing. But there's some handy shortcuts that you can see from this menu. What I personally use is, so I will need, press Shift and Enter. So yeah, this is what I will usually use, which is the same as clicking that Run button, and you just do a Shift and Enter. If you want to also insert a cell, then you do Alt-Enter. When we say insert a cell, we mean when you want to, let's say, beneath this one, I go Insert, and then I go Insert a cell below. The default is that it's going to open a code cell. If you look at this one, this is a Markdown cell, which is basically for writing text and like explaining what's going to come after in your code cell. You can go here, there's different options to it. These are the only ones you're going to need to worry about. Now, if you added a cell and I didn't want to add one here, you can simply go here, delete it, it goes away. Definitely encourage you to look up different, so cut cells is just Control X, which is what you'd expect. So let's try that, do an Alt-Enter, and then if you want to cut it, just do Control X. It has to select the cell and function. Sorry. So I'm not going to go over the homework notebook because that will be cheating. We will see some Okay, yeah, before I move on, however, though, you can save your notebooks. You don't need to, like Julia will, like the server will save your notebooks for you, but in case you want to save it, you have a local installation and you decide to save your notebooks, there's a way to save it as a notebook.ipython notebook. What else do we have here? Sometimes you might see over here, it says Kernel Disconnected, which basically means, sometimes it basically means that you were just not working on your computer, you just had it on, and the server times out after 30 minutes. So if the screen has been inactive for 30 minutes, you'll sometimes see that it just says server disconnected. The way to fix it is basically just go to server, you can restart, and there's different combined options with it. You can restart and run all, you can restart and clear output. It's a bunch of stuff that you can do. So if there's any doubts as of now, anything else you want to share, you guys found a cooler option that I did not go through. Yeah.
So say if we submit the assignment and when we click like touch feedback, it's like everything looks good as like an assignment.
Mm-hmm. That's what you want. Did you submit?
Well, yeah.
Did you submit? Okay, good, good. So, well, before we do anything else, you can upload files. So if I had a notebook in here, which is, yeah, I can do this one. I can upload this over here. So if you've saved stuff locally, there's ways to upload it and run it. And then you can do whatever you want with it. If you want to open a completely blank new Julia kernel, the way is to just go here, click on New, and select Julia. It'll take a while because like the kernel restarts every time you open a notebook. But you can do the basic stuff like print hello world, and then Control Enter to run the current block. So I think that's about it for, oh no. There's also questions about people that are having trouble with submitting your notebooks. So the way to submit it is just go to your assignments where we found the Fetch tab. There's also the Submit button. So once you finish your homework, just submit. And there wouldn't be any feedback as of yet because I just submitted. But that is the idea. You can refresh it if you want. And yeah, that's about all you need to know about a Lumidesk. It's very handy to use. It took us quite a while to land on this solution, but we're very happy with it. So let's go back to basics of Julia. Again, there's just when I say do a local installation, you also have to remember that whatever packages you're going to need after you've done your local installation, you'll have to install them yourselves. And some of these packages can be tricky to install, so it's completely on you. If you feel comfortable working on a local machine more than a cloud-based thing, then go for it. But you've been warned. And that was the wrong button. So, talking about packages, packages are basically predefined functions that other people have written for you. So let's say you wanted to plot a line plot. Now, either you can do a lot of low-level programming the way Julia does it, or you can just call using plots, which is the name of the package that you want to use, and then it brings with it a bunch of functionalities, which lets you to call a function called plot and give it another function called sine, where the x value ranges from minus pi to pi, and then plots the value against a y. But you don't need to worry about that unless it's just a cool functionality to use. There's many different ways of plotting stuff that we will go into through the course. Now, another way to write readable code is with all of these codices, you want to write comments about what your code is doing. So in Julia, we write comments with a hash, and we do multi-line comments with hash and equal to. So if you were to write something like this, the compiler will ignore all of this that's happening here, and it'll simply execute it for you. Multi-line comments, if you were to not put the equal to sign, it'll think that this is code, which it's not. So this is how you will use multi-line comments. Arithmetic operators. So I think the first homework that we have is just using Julia as a calculator, which lets you do a bunch of arithmetic operations. So you can do addition, you can do subtraction, you can do multiplication, division. You can also remember the answer from the previous code cell, refer to it as you would do in a calculator. There's ways to round your numbers. So there's a function called round. We know 22/7 is pi. And then you can also specify precision with digits equal 3. And it will only limit the value to 3 decimal places. There's exponential, which is 2 to the power 5, which is how you'd write it in math. There's square root. And this, if you've done programming before, you're aware of the modulus function. So this will just return the remainder. So 5/3, so 3 times 1 is 1, the remainder is 2. You can also use it for floating point numbers, the decimal numbers. It'll give you a good result. The other version of it is just using the word mod. You can use the percentage, or you can use the modulus, or called mod in Julia. And it'll do the same thing for you. There's another thing that not a lot of languages have. It's called integer divide. And it's exactly what you'd think. It's like writing math. It's 4 divided by 2, and you get the integer of the division. That was probably not a good example. Another interesting thing about Julia is that when you work with C or Python, you don't really get, you don't see fractions as such, but Julia lets you save stuff as fractions with, so 1/2 will be written as 1//2. And that's a rational number, which is like a completely different type that we can look into. Now, when you're using arithmetic operations, you have to take care of the precedence, which is how you'd learn in math as well. You can't expect -2 times 3 and just be like, oh, but I wanted to do that. So a good thing is to use brackets to make sure there's no unpredictable behavior in your code. So if you wanted to do 3 times 4, this is not the way to write it, because you will first evaluate 2 by 4 to be 0.5, and then you'll add 1 to it. So if you had to do 3 by 4, you have to use the brackets. Now, once you have a way to do calculations, what makes it different from a calculator, I guess some calculators can also do this, but you have the ability to do numerical comparisons. So you can check for equality. Is 2 equal to 2? Yes. Is 2 not equal to 2? False. Is 3.5 greater than 2? Yes. Is -1 greater than or equal to -1? Yes. Is -1.0 less than -1? No. And so on. What you should note from this is the equality thing throws a lot of people off. If you put like a single equal to mark, it'll always be true. And if you use a double equal to mark, that means you're checking for equality. There's other mathematical operations that you can just use. You should also check out the precedence of all these operators so that you don't have unpredictable behavior in your code, and you know what functions to use and not to write a completely different function for converting from radians to degrees. They already have it. Getting help. So when you're learning a new language, you're going to be thrown a lot of words, a lot of functions that you're going to be wanting to use. So an easy way to query Julia about functions is basically just you put a question mark, leave a space, which opens the help module in Julia, and then let's say I want to know what the function radians to degrees does. And as you would expect, it converts whatever you give as an argument from radians to degrees. So radians to degrees of pi is 180.0. I feel like I'm ignoring people on Zoom. We're good, right? If you're here. I'm gonna assume they're here because I can do what I want. So there's also the function called GCD, which does exactly what you think. It gets the greatest common divisor, which is what we learned in high school. So yeah, the idea is whatever you need to know, whichever function you see in a code and you don't know what it does, just put a question mark in front of it, leave a space. The space is important. And then put the function in there. Displaying results in Julia. So if you were to run this code cell, it will not give you an output because you see there's a semicolon in there. So Julia is kind of like MATLAB in this sense. So if you put a semicolon, it's not a display thing. So if you want to display, avoid the semicolon, first of all. Another thing is, if it's a single block of code that you're running, it'll only return the value of the last evaluation. So what if you wanted to see 3 and 7? So you're going to need to explicitly write print statements like you do in, I want to say Python and C. So these are two comparable functions. One is just display with, what's it called? There's a term for it, display with pump and show. It's like a bigger display, and just a simple print line. So now that we're over with like functionality, we can look into how we code. So first thing that you want to do when you're coding is you want to define variables. The naming for Julia is that your variable names have to start with an alphanumeric thing. And alphanumeric basically means it's either a letter or an underscore. You can have numbers in it, but the numbers cannot start the name of your variable, which is what is the convention for most languages that you'd learn. Variable names are case sensitive, so we'll have to take care of that. So you can define a is equal to 10. You can print it, and capital A is 11, and you'd see those two are different variables and it can recognize it. But you can't have a variable begin with a 1, which is what we discussed, but underscore is okay. Now types. So one way that Julia has helped us all is that we don't have to explicitly declare our types, which is what people have to do in C++. And it's a lot of work, but what makes Julia easy to use is that it will implicitly find out the type for you. The types that we're going to be working with mostly are integers, floating point numbers, and strings. Now, there's different types of integers, and they're which depends on like how much memory they're going to use. So there's 8-bit, 16-bit, 32-bit, 64, and 128. And because of the memory constraints, which it also means that the range of the numbers that you can accurately represent in that range is different. So for an 8-bit number, you can go from -127 to 128. And that is because when you represent them in binary, you'll see that is the range that they are able to represent. But you don't have to worry about that if you don't know how to represent it in binaries. These are just ways that the computer saves all of your input. By default, however, Julia is going to interpret, so if I say a is equal to 10, it's going to interpret it as a 64-bit variable. So the way to see a type of a variable in Julia is simply to call the function typeof. So you've got a is 10, and then type of a is float 64. So it's a floating point number because I put the 0.0 in there. If I did not put the 0.0 in there, it's an integer, and it's an int 64. If you know the distinction between these two types, we're going to be fine. Then you should also notice, so a was 10. Yeah. An integer divided by integer, you will still get a decimal unless you do an integer division, which is what we saw before. And you'll see the type of C is float 64. So you want to be careful of your types, even though Julia is pretty okay with typecasting between different kinds of variables. Sometimes it can give you unexpected method errors, which is a lot harder to deal with than you'd think. Integers, however, when you add them, they still stay int 64. So when you do a plus b, it's still int 64, which makes sense because that's how we do math, right? If you say d is, we learned this was the way that Julia expresses fractions. So you'll see d is a rational int 64, which is unique to Julia. I don't think I have personally seen it, and I know C, Python, and MATLAB Nobody really has a rational data type. You can also express complex numbers. So 3 plus 10i, which is the iota that we know of, can be written as 3 plus 10 im. And it will interpret the type to be complex, so float 64 because of the 10.0 in here. And then it'll also, even if you look at the real part, it will typecast the type of the, it typecasted your integer 3 from 3 to 3.0. So when I check the real part of E and I check the type of it, I get float 64 because it typecasted it for you. Questions? Am I going too fast, too slow? Am I just perfect? Yeah? Okay. So like we were talking about, you want to be, sometimes it's easier to deal with types if you explicitly know what types you're dealing with. So there's functions that you can explicitly convert between types. So surprise, it's called convert. So if C is 10.0 and I want to make it an int 8, I will simply write convert, the type that you want to convert it to, and then the variable. And then you check the type and you get int 8 exactly. You can also do, instead of writing the type down, you can just infer the type from another variable, and that will work just fine. Moving on from that, the other data type that we have to be worried about is we're going to be dealing with strings. So like most programming languages, Julia represents strings in double quotes and a character in a single quote. So you can say C is equal to hello world, and the type of C will be inferred to be a string. Another problem that you're going to deal with is concatenating a string. So we use the multiplication operator. In object-oriented programming, we call this, I think, polymorphism. The fact that you can use one operator and it will infer the function from like the different operands that you give it. So if you give it 2 integers, it'll know that you want to do a multiplication, and if you give it 2 strings, it'll do concatenation for you. One thing to note here, it doesn't give you a space. So if you want to have a space, add the space that you want. Or you could use the string function. So just call string and then separate whatever you want to concatenate with a comma. What the concatenation using a star will do is just take 2 strings and give you a concatenated string. But with the string function, you can also convert integers, Boolean, all different kinds of variables into a string. So if you had to do C is equal to false, then you can do something like this, and it will concatenate A and this integer 1, and then this Boolean variable false, and give you 1 string, which is sometimes useful when you're writing down files and stuff like that. You're going to use it a lot. So in summary, why we use Julia? Because it's easy to write, it's easy to share, it's easy to plot stuff in. It's one very good built package that lets you do everything from prototyping to actually visualizing stuff. And at the same time, you can do it on real systems, so it's as powerful as C and Fortran. You comment using hash and the multi-line using hash equal to. There's packages that you can use using the using operator. There's arithmetic operations that we've learned. There's numerical operations that we've learned. You get help using the question mark, and then these functions is how you display stuff. And we also know how to build a string. This was like a very, very, very tiny overview of Julia. What we're left with is we want to learn how to build matrices, arrays. We want to learn how to plot stuff. We want to define functions, structures, and we want to control the flow of our program using if, then, else, and we want to do looping, which is not something we're going to do right now. We're going to do it once we need it. And that is it for today. Do you guys have any questions at all? No? We're good? Any problems with the homework? No? Ansh, are you good?
So it says like optional stuff, but like when it says like can you relate the results of your graph to the following systems of linear equations? Like what is it looking for?
Oh, so it's looking for like what we did. Like you plot stuff, and then if you can find a unique solution, then you're supposed to be able to see that from our graph, I find that this is the solution. And then you see your analytical solution, and you should be able to compare that those two are the same, or at least similar. Yeah. No problem. Now, you guys are free to stay and follow along, but for people that are watching this asynchronously, I promise that I'll do quadratic equations. So I'll go over one example. Follow along if you want, or not. It's a free word. So, quadratic equations. Let's do the last example where the roots are complex, because I feel like that's the most interesting one. So, you get our equation is x squared minus 10x plus 26 is 0. From our closed form solution, we know how to find the roots of the equation. So your answer is, well, I want to get this thing down first. So for ax squared plus bx plus c equals 0, we want to be able to plot y is this equation, and this b squared minus 4ac is our discriminant. Thank you for coming. And we're going to want to solve for roots of x. And from there we take a from ax squared plus bx plus c equals 0. We can infer a is 1, b is minus 10, and then c is 26. And so you write From our formula, we get x is minus b plus minus underscore b squared minus 4ac, the discriminant. And from there, you get 10 plus minus under root b squared is 100 minus 4 times a is 1, c is 26 by 2 times 1. And then this becomes 10 plus minus under root minus 4 by 2. The discriminant from here is minus 4, which is when you note less than 0, and when we know the roots are, when the discriminant is negative, we know that the roots are complex. So from our equation, we know that our roots are complex and imaginary. So the way to go about it is I take the 4 out of it, and then I know under root 4 is 2, so it becomes 2 times 1 times under root I by 2. We also know that under root minus 1 is denoted as I and is a complex number. And so here you have our roots are 5 plus I and 5 minus I. And to define our parabola, we need 3 points to be able to uniquely define it. The way to do that is we want to plot y is our equation that we just solved, and from there we will put different values of x in there and we'll get different values of y, plot those points, and then make a parabola. So you put the roots that we found before analytically, so we know that this should be 0, right? So we found the roots to be x is 5 plus I and x is 5 minus I. And just as a sanity check, when we put it in the equation, we get y is 5 plus I whole square minus 10 times 5 plus I plus 26. Now remember, I square is equal to minus 1. So this becomes 25 minus 1. Minus 10 times, plus 10 times I minus 50 minus 10 times I plus 26. Lo and behold, these two cancel out. You get you get 25 minus 1 is 24, plus 26 is 50, and then 50 minus 50 is 0. So I'm going to remove all of this because we know how to do this, and I'm just going to put what we found, which is y equals 0. Similarly, when you'll put 5 minus I, you'll get y equals 0. Now, you have 2 points, but I don't quite know how to plot 5 plus I comma 0 and 5 minus I comma 0, because those are complex numbers and you can't find it on a real x-axis. So we're going to need more points than that. So the way that I would do it, I would get the value of it at the midpoint on the x-axis from my roots. So for x is equal to 5 plus I, I'll want to find it for x equals 5 plus I, 5 minus I by 2, which is basically just 5. So let's put x equals 5 and x equals 0 in our equation, and you get y equals 1, and from here, just putting in this equation, this is 0, this is 0, just left with 26. Now these are points I can plot. I can plot 5, 1, and I can plot 0, 26. Now I have 2 points. I need 1 more so I can make a good parabola. So what I'm going to do is, actually, if you think about it, with the axes that I have set here, it's kind of hard to plot 0, 26. So I'm going to assume I only have this 5, 1. So I'm still lacking 2 more points. And a good rule of thumb is go to 2 points that are like equidistant from your x-axis, especially if you know that the graph is like that. So that's what I'm going to do. So I need more points. And I'm going to choose those points to be x equals 3 and x equals 7. And from there, replacing them, I get y is 5 for both of them. It's just putting it into the equation. And your points become 3, 5 and 7, 5. And if you were to plot these points, I feel like I moved. Let me just move it. Let me just move it here. So if you were to plot them, first of all, I'm going to plot 5, 1. So 1, 2, 3, 4, 5, and 1. So this point right here. Next thing, I want to plot 3, 5. So 1, 2, 3, 4, 5. And finally 7, 5. So 5, 6, 7, 5. And then a line that goes through these points is not a line, it's a parabola, I'm sorry. I'm going to do my best to draw it. And I did not draw it the best way I would have liked, but you get the idea. And so from here, you can see that the graph doesn't meet the x-axis at any point. So your roots are complex and you can't see them meeting anywhere on your x-axis. It's kind of like a floating graph. And once you actually plot these two, the problem has been designed in such a way that you'll find the first one and the first one has two distinct solutions and the second one is repeated roots. And I think it's a good exercise to try and plot the two, and I encourage you all to do it. And that's it for today. Thank you for joining.